Yes, I was saying, if you didn't log in, I changed the deadlines for some of the assignments on my lab. So now you have the weekend to work on those. If you, let me just start by reminding you what we were doing yesterday. So let me share my iPad. Oh, uh, yeah, it has been a problem. I mean, and strictly speaking, like, I don't really know who is attending since I cannot see your cameras. So for all practical purposes, you could all be watching Netflix, and I don't even know. I mean, I could just be talking to like three of you. So that's fine. This is why I don't know if you saw this Facebook proposal for like Zoom meetings, where like it would be like a virtual setting. And so you go in like, it probably won't work because people want to use the fact that you can just do something else when you are like in a Zoom meeting. So if you have to actually see everyone on, virtually, then you really know if someone's paying attention. I think people got used to like just like turning off of what's going on. So yeah, but some of you are present because there is some chat. So, but yeah, I don't know how many. So let me remind you what we were doing last time. So if you have two vectors, and there's some angle between them, which we call theta, then the dot product, is just by definition, if you want, the product of the magnitudes times the cosine of the angle between them. This is like an important formula we use many times in the class. One of the key properties, like what we were discussing, were some of the properties of the dot product. And one that you should really remember is that if the dot product is 0, right, then that means that the vectors are actually perpendicular to one another, which we also call orthogonal. So the vectors are perpendicular to one another. Okay, now the other important property, which is what we were discussing, is that if you have like XYZ, right? If you choose like the origin, and you can like find like three very important vectors, which are called the vectors I, J, and K. Okay. Well, some reasons why they are important is that, for example, as we said last time, since they like sort of are aligned with the axis, then they're mutually perpendicular. So that means that I dot J is the same as I dot. Oh yeah, like you mean like the something like that. And you can also use that one. It's just to keep putting like an arrow for everything that's a vector. But yeah, that's you can use that one as well. As I said, like in practice, if you were actually writing this like on a computer, like everything will just tends to be written in bold letters when they're vectors. So usually like even ij and k, sometimes you just see them. That depends a little bit on which how advanced the book you are using maybe. But yeah, like there's no ambiguity if you want to put like the arrow or the other thing. So they were mutually perpendicular, and something that I didn't say, but it's good to maybe you already know what the answer should be. But what is I? Yes.
One quick question. What do you mean by ij is equal to ij? Is that supposed to be k?
Oh, good. Yes, excellent. Good, thanks. Yes, now it's better. Thanks. Now, for example, what is a dot product of I with itself? If you use the definition, right, it would be the product of the size of I times the product of the, I mean, you multiply the magnitudes or the norms of I times the cosine of the angle of I with itself, right? Now, what was the size of I? It was 1, if you remember. So you get 1 times cosine of the angle. But what's the angle of a vector with itself?
0?
Yeah, right. If you sort of have to make a copy of the vector, right? Like imagine just drawing like I here, and you do like a clone. And so yeah, what's the angle between them? Is just cosine of 0, right? Which is also 1, right? And so you get 1 times 1 times 1, which is 1, right? And so the same would happen. I mean, you see that the same happens with j dot j, and the same happens with k dot k. So these vectors are convenient because sort of they kill each other, right? In their dot products, like they don't see each other when you take their dot products, but when with themselves, they just give you 1. So let's just put this like in a box. This is again, if you take something like linear algebra, you say that ij and k are like a basis or for the vectors, but it's not something that we'll like a term that we will use. So let me just also write here I dot I equals 1. And so for example, how does the formula for the dot product work in practice? So here's how to find the dot product. Well, say if you had like u, which is like a vector which is 2, 3, 5, that's really the same as 2i plus 3j plus 5k. Just because you know, I is like 1, 0, 0, 3 is like j is like 0, 1, 0, and k is 0, 0, 1. So if you just do the multiplications, you get back these entries. So that's like another reason why ij and k are useful, because you can just like break this thing into 3 pieces. And likewise, if I gave you a different vector, you can still break it in the same way. So you get something like 2i plus 4j plus 6k. Is that making sense? Is that okay with everyone? So you can just read the numbers, and that's what's multiplying each of the ij's and k's. And so if you wanted to do the dot product between them, this is just the same as 2i plus 3j plus 5k dot 2i plus 4j plus 6k. But as I was trying to explain last time, what will happen is that like there's a bunch of things that die. So you have the red ones, so this would be like the red stuff would be like 2 times 2 I dot I, or like, yeah, I put it like this, plus 2 times 4 I dot J plus 2 times 6 I dot K. Well, actually, you could arrange it in a matrix if you have seen that, although it's not something we would do. But yeah, it's sort of tempting to put like the coefficients that I'm writing as a matrix. But it's not, I mean, not something that we would do, but like, right, I'm writing it in a way that sort of suggests that that could be something you could try to represent it by. But yeah. In fact, we won't really use matrix in this class, so too much. Someone was going to say something, or oh yeah, it's going to be well, it is a magnet. It depends by what you mean by the magnet. It is the product of the magnitude. It is the product of the magnitude times the cosine, right? I'm just giving you like an alternative way to find it. So I'm saying like this is a different, I mean, you could find it this way, but if you want, you can just find it the way I'm doing it right now. So, and you'll see that this is actually more useful in practice. Here, let's put the other one. So then you put like 3 times 2 J dot I plus 3 times 4 J. This is like one of those things that one does one time in your life, and then you never do this again. But it's sort of for people to see how it actually pops out, like the actual formula. So it's not that you have to really do this every single time. I mean, I'm just trying to show you how it actually appears, and then you just forget. I mean, and then I'll write the formula, and that's like what you keep using. And then you do 5 times 2 K dot I plus 5 times 4 K dot J plus 5 times 6 K dot K. Is that making sense? Yeah, exactly. That's what's going to happen. So you see, there's a bunch of things that just die. Why do they die? Because many of these dot products are 0, right? So this is 0, this is 0. In fact, if you again thought of this as a matrix, for those who have seen it, whatever is not along the diagonal just dies automatically. So a priori, we had like 9 things that we had to add. Like 6 already die automatically, and the others are simplified significantly. So because so let me just put that this is 0, 0, 0, 0, 0, 0, and the others simplify a little bit because I dot I was 1. Well, the matrix, like if you would only like the matrix, you would just put like it would be like I mean, you could think of a 3 by 3 array where this is like the first entry, the second entry, the third entry, the fourth entry, the fifth, sixth, seventh, eighth, ninth entry, if that helps. So it would just like, if you have like, you write it, you could write it like that, but it just that you don't gain too much by doing it. Oh, how do I know that these are 0? Because we had computed a bit earlier. You see that all these dot products were 0 because they were perpendicular. Is that okay? Yes, this is always going to happen, and that's why I'm saying like you don't have to do this same procedure every single time. What I'm just showing you is that like why the formula that I'm going to write soon is the one that actually works. And then when you see this, right? Oh, someone was going to say something.
Yeah. So, Professor, the perpendicular equals 0. That's just the general rule of thumb for everything, right?
Right, yes.
Okay.
If the vectors are perpendicular, their dot product will always be 0. And you just happen to know that ij and k are mutually perpendicular, yes. But in general, you could have other vectors, and if they happen to be perpendicular, their dot products will be 0, yes. And then for these other three things, right, it was like I dot I, J dot J, and K dot K, and that gave us 1 because that's exactly what I wrote here a little bit earlier, right? So yeah, someone noticed, you just end up getting like 2 times 2 plus 3 times 4 plus 5 times 6, and that's 4 plus 12 plus 30, right? Hopefully. And then this is what, 16 plus 30, what is that, 46? And so that's that product. And so what you like to summarize, what we had is that if we had 2, 3, 5, and another vector which was 2, 4, 6, when you want to do their dot product, you just multiply their entries, right? You just sort of put like match their entries. So this one with this one with this one, and this one with that one, and then the dot product is just like what you get by adding together the results. So you get 2 times 2 plus 3 times 4 plus 5 times 6, and that's 46. Is that making sense?
Just a quick question, because this is a little bit reminiscent of what was done in statics when we did the dot product. There we used some kind of cross rule where you would say you would multiply the 2 by, like, you see how you have the u and the v vectors set up with their I, j, and k components.
Oh, are you thinking like the cross product?
Oh, okay, yeah, never mind.
Yeah. This will appear in a couple of minutes in today's lecture, but it's somewhat.
Okay.
I mean, right? Like you can present it in a way that looks similar. Yes.
Got it. Thank you.
Yep. But right, in general, so this is like the general formula. If you had like two vectors whose like entries are like u1, u2, u3, and another vector which is v1, v2, v3, then if another way to compute the dot product is like what I'm saying is that u dot v is the normal view times the normal v times the cosine of theta, but that at the same time, that's equivalent, that's the same as doing u1 v1 plus u2 v2 plus u3 v3. Okay, I'm saying like either of these two formulas can be used for the dot product. So the thing is like, this is sort of easier to use if you are given like the vectors with their entries. So this is a little bit better, like this is more convenient. This second formula is more convenient most of the times, so. Is that making sense? Are there any questions about this?
That makes sense.
And so this is so this, like, let me just put it like this, this second formula usually tends to be more convenient. Right, the matrix, like, I mean, there's a like the cross product, like the formula I'll give you soon is you can rewrite it as a matrix. I'm just saying, I was just saying that, right, if you write this expression this way, it sort of suggests that you could write like coefficients in some matrix, but it's never done because most of the things are always 0 to begin with. So it's not like, it's over like it's like an overkill, you see. So because so many things die that you might as well just keep the things that you care about, and that's so much easier like just this way. So it's never really written as some sort of matrix, like. So this is like tends to be more convenient. So for example, here's another property of the dot product. So if you have a vector, right, v, I mean, this is essentially the same that we did with I dot I. What would v dot v be equal to? Well,
Zero.
let's, oh, you have to be careful. We have the two formulas, right? Yes and no. Okay, so let's go to the first formula, right? Like that, can everyone see like the cloud, like where I'm pointing this for? Everyone can see the pointer, right? So what's v dot v? It would be the normal v, right? Times the normal v times the cosine of the angle, right? But what's the angle in this case between v and itself? The angle is 0, right? So it's cosine of 0. Is that making sense?
Yeah.
Mhm.
Professor,
Yes.
I was wondering how you would figure out the angle between U and V in the previous problem if you wanted to do it with the first method.
Oh, here?
Yeah, exactly.
Oh, actually, this is funny. Like, if you wanted to know the angle here, right, between those two vectors, like, and I'm actually going to say this in a second, you sort of reverse engineer. So, like, I will write it and then delete it because I'll mention it later. But you can use a formula of the dot product to say that the angle is u dot v divided by the products of the norms. You see?
Oh, okay. So you would never like,
Yeah, you sort
find
of
the
cheat.
answer
You
using
sort
it.
of cheat, like, because it's, yeah. So, but I'll do it in an example soon. But yeah, that's a good point. Like in practice, like sort of the way to find out the angle between two vectors is almost by using the formula for the dot product. So, but I'll say that in a second. It is what's going to be the next thing I was going to say after this. So everyone is okay with the with this, that the dot product of v with itself is v squared. And the size, like this means that the dot product of a vector with itself is the square of its size or its length. Is that okay? But at the same time, that's like, this is with the first formula for the dot product that I gave you, right? But let's use the second formula for the dot product. What would v dot v be? That's v1 comma v2 comma v3 dot v1 comma v2 comma v3, right? And if you write it this way, it's like, again, like everyone multiply the corresponding entries and then add them together. So you get v1 squared plus v2 squared plus v3 squared, right? Is that okay?
Yeah.
But you get like, right, like these two things are the same thing, right? Like the red stuff and the blue stuff are the same. So that tells you that the size square of a vector, right, is what? It is v1 squared plus v2 squared plus v3 squared, which tells you that the size of a vector, right, is the square root of v1 squared plus v2 squared plus v3 squared. And does that look like a familiar formula?
Yeah.
That's just Pythagoras, basically, right?
Definitely.
So you see, you sort of found without noticing, like knowing it, like Pythagoras theorem, kind of. So let's call this 3D Pythagoras. So with this, like, again, like probably something you knew how to do before, but so if I give you, let's do some examples. If I give you a vector, if I give you a vector like 1, -2, 5, I ask you, what's its norm? What's its size? Well, yeah, it's just the square root of the squares of the entries added together. Is that okay with any questions? So far, so good.
All good.
And now, and like, for example, I don't know if you remember, was it yesterday, that I had given you like this formula that said, like, if you have a point, oh, sorry. If you have a point P, if you have a point P here, which is x1, comma, y1, comma, z1, and a point Q, which is like x2, comma, y2, comma, z2. I don't know if you remember from yesterday, I think that there was this vector PQ, which went from P to Q, right? So this was, I think, yesterday. We had this vector PQ from P to Q. And if you remember, the formula was Q minus P, which is x2 minus x1, y2 minus y1, and c2 minus c1. Let me just write this a little bit better. Right? And the size of this blue vector was supposed to be the distance from P to Q. But now we know how to find the size of, so the distance from P to Q is equal to the norm of this vector PQ. But because of the formula that I just gave you, you know, and again, this is probably things that you have seen before, but now we're looking at them from a different perspective, right? Is that making sense? So that's like how,
Looks like the distance formula.
yeah, it's just like the ordinary distance formula that you probably saw in high school, right? But I'm just saying we are sort of like thinking about it like as having been obtained from with the help of the dot product somehow. So it's not something new, but in the same way in which like this Pythagoras formula or theorem is probably something you had seen before, but it sort of appears in a different perspective if you do it through the dot product. Okay. So far, so good. Any questions? Okay, and then for now, the last thing I want to say about the dot product, and then I'll say something else about it next week, is the following, which is this question about the angle between two vectors. So let's talk about a little bit more about the angle between two vectors. So if you start like, again, if you have these two vectors, u and v, then we know that from the formula of the dot product, the dot product of u with v is the norm of u times the norm of v times the cosine of the angle. And the point is that if you somehow know how to find the dot product and know how to find the norms, then you can actually use this formula to find the angle. So you sort of turn things around and now say, well, what if you divide both sides by the norm of u and norm of v? Is that okay? and so that gives you like a formula for the cosine of the angle. And then if you take like cosine inverse or arc cosine, then this actually gives you like the formula for theta. So theta equals the arc cosine of u dot v over norm of u. No. Is that making sense? Is that okay with everyone? So let's do an example. So let me do an example here. Let's say that you were asked to find the angle between these two vectors. Right? So if you just look at the formula, the angle, and this is like a formula that again is like a very important one. It's essentially the same formula as a dot product, but just seen in a different perspective. So from this formula, you shouldn't forget it. So it's just the arc cosine of the dot product, which would be the dot product of 1, 1, 1 dot negative 1, 2, 5 divided by the size of 1, 1, 1 times the size of the vector negative 1, 2, 5. But now we know how to do all of these things, right? The first dot, the numerator, what is it equal to? Remember, you multiply all the entries. So 1 times negative 1 gives you negative 1. 1 times 2 gives you 2. And 1 times 5 gives you 5. And the other one is like the square root of 1 squared plus 1 squared plus 1 squared times the square root of negative 1 squared plus 2 squared plus 5 squared. So you get the arc cosine of what? This is 6 over root of 3 times what? Root of 30? And well, whatever that angle is, it is what it is. Oh, right. This is similar to what we had talked about when I don't know if you remember when we said how would you, that you cannot really add, you know, a vector which has 2 entries and a third vector and the other vector which has 3 entries. So you cannot, if you are going to do the dot product, they need to have the same number of entries. You can cheat and like add like a 0, you know, like for this one, if it had 2 values, 2 entries, you can add a third entry and take it to be 0, right? And then, but then so somehow that way you made them of the same size, but they do need to be of the same size, even if you need to do a trick first. Is that making sense? And well, you don't like sometimes right, no, in this case, like the answer, like you would just leave it, you can just leave it like this. You don't need to simplify it further. Like this is something that MATLAB would understand in principle. So you don't need to approximate it or try. I mean, I guess it's clear that this should not be any of these special angles. So you can just right on my lap. Oh, that's the answer. But yeah, in principle, they are all in radians. So this is like the answer in radians. Like whatever that angle gives you. Yeah, you should like there's really not like a calculator on the exam, so yeah, you would not have to simplify this anymore. Is that okay? So far, so good. Any other questions? But so yeah, this is basically how you use a dot product to find the size of a vector and to find the angle between vectors. I mean, there are other things you can do with dot products, which are a little bit more interesting. Like you could define dot products, for example, between functions. So you can define like a dot product between the function sine and the function cosine. Those end up being 0. So for those cases, so then that means that somehow those two functions are perpendicular because their dot product is 0. So you can I may ask you to watch a YouTube video for the optional question on the quiz about that. So, but yeah, you can sort of use like try to define like a dot product for functions, and so that allows you to talk about the angle between functions, like the angle between y equals x squared and y equals x. That's also something you can do. So just switching gears a little bit, let me talk about the other way to multiply vectors, which is this cross product stuff. This is more like roughly about section 12.4 on the book. So this is about the cross product. As I said, there's something that I still need to mention about that product, but I'll say it on Monday. So any questions? So here, you have two vectors u and v as before, and now we're going to define a new multiplication between them. So we're going to define something that's called the cross product, which is u cross v. Okay, this is called the cross product. Okay, and basically the idea is that in the dot product when you did the dot product you got a number. This is when you do the cross product you actually get a new vector. So this gives you a new vector. Okay, and this new vector has a property that it is built in such a way that it is perpendicular to the original two vectors. So whatever it is, it will be a vector perpendicular to. So this is a vector perpendicular or orthogonal, right? To both u and v.
When you say that, how can that be since u and v both point into different directions? Is that only a component of the new vector that's perpendicular?
Well, no. Like here's the thing: you have u and v, right?
Yep.
they're like again doing their own thing in space, right? If you want to find their cross product, you have to bring them together first, right?
Okay.
Once you bring them together, there's actually like, let me bring more toolkits. Once you have two vectors together, you know there's always like a piece of paper that where you can draw them onto. Does that make sense?
Yeah.
So I mean the technical terminology is that they belong to a plane, right?
On the same plane. Yep.
Yeah.
Decoplanar.
And then once you have a piece of paper, right, you can find a vector that's perpendicular to the piece of paper, and that's how.
Oh. Okay, I see it. Okay, that makes sense. Yeah. So it's perpendicular to the plane.
Right, it's actually ends up being perpendicular to the plane, to the paper that contains both vectors, if you want to say it
Got it.
that way. Yeah.
Okay, understood.
Is that making sense?
Yeah,
So,
thanks.
well, right, this is like this is a like this is mostly for vectors with 3 entries. There are other things that you can do when they have more entries, but it's not quite the same. It goes through a different terminology. That's yeah, like think of them like really, like I'll specify this, like really this is defined in the easiest way just when the vectors have 3 entries. Which is good because the course is mostly about 2 or 3 entries. If the vector has 2 entries, then you do the trick where you add a 0 to the 3rd entry. So really, that's fine. But yeah, we're not going to, not that we're going to use vectors with 4 entries, but it's not like there's like what counts as a cross product is more complicated than what I'm going to give you here. Yeah. So what I was saying is that, yeah, like the cross product is supposed to be a vector like that's perpendicular to both U and V. Is this making sense? So, but yeah, this is sort of what someone was just mentioning on the chat. So if you have these 2 vectors, right? I'm saying, oh, this is perpendicular to these 2 vectors, right? But someone could, for example, point out, well, but isn't this other one perpendicular to these 2 vectors, right? Everyone sees that there's some sort of ambiguity. Like, how do you choose which perpendicular vector you want to use? Is that making sense that there's more than one option?
Yeah.
So there's like a convention to decide this, which is called the right-hand rule. And so the right-hand rule is a way to sort of sort out which of the 2 vectors you're going to choose. So in order to, so let me put this here. There's a way to decide which of the which direction for the vector you want to use. Now, there are multiple ways to explain the right-hand rule. Let me, like, and not claiming that the one I'm going to show you, I mean, this is the one that I always found easiest, but like, feel free to like, there, like if you go to Wikipedia, you'll see it explained like in 3 different ways. Again, like in practice, it's not that you're going to be using the right-hand rule really to find the cross product, like, because there will be a formula in terms of the entries, which will give you the answer. But this is sort of for you to know how it is done in other places, like in the physics classes and things like that. So say if this is a vector u, like what I would do is like put my fingers pointing along u, and then I would close my fingers towards the vector v, and then my thumb would give me the direction of the cross product. So I just curl my fingers towards v. So you're not going to use it. Oh, the cross product will appear a couple of times. Yeah, but again, like you won't use it. We won't use it like where we find it with the right-hand rule, for example. We'll find it in a different way. So, but what well, yeah. So let me couple of questions. So, well, it depends, I guess. Like I think that the thing about z I'll answer in a second. V cross u would be in the opposite direction. Good. We're getting close to many truths, right? So like what I'm saying is that if you were to do u cross v, you sort of move your fingers like from u to v, and the thumb then gives you the direction for u cross v. But yeah, someone just pointed out, let me write them both next to one another. So here, if you have u, and here you have u, and here you have v, and here you have v, right? So for u cross v, you have to go from u to v. I think that's not a question, right? What is it? So that's u cross v. But if you were to do v cross u, right? Then this is u cross v, right? But if I were to do v cross u, then now I have to put my fingers along v, and then I have to close up towards u. And so I don't know if you saw that my thumb changed directions. So v cross u actually goes the other way. That's right. And they're actually the same size. So is that making sense? So if they point in opposite directions, one is like minus the other, right? So this is actually like an very important formula not to forget ever in this class, that v cross u, for example, is minus u cross v. So don't mess around with the order of the cross product, right? If you like, it does matter in which order you write it. So it does, the order matters. Is that okay? Now, and I have been telling you a bunch of things about how to find the direction, but remember that a vector has both a direction and a size. I still need to tell you what the size of the cross product is. So the size of the cross product is taken to be the product of the norms times the sine of the angle. So that's like to fix the size of the cross product. So it's like the formula for the size is very similar to the one for the dot product, but the dot product uses cosine while the cross product uses sine, okay? So far, so good. So these two things are the key properties of the cross product. And from here, we can already start finding other things. So for example, let's go back to our friends from before, which were ij and k. So here you have I, here you have J, and here you have K. So what do you think, for example, I cross J would be?
Okay.
It is K, right? Because again, let's say the x-axis is pointing this way in my screen. So it's like I cross J, and so you see my thumb pointing up. So it gives you K. And once you know that, you actually know without more effort what J cross I should be. What should J cross I should equal to?
Minus K.
Negative K?
Yes, because you just flip. You see, if you change the order, you just have to put like a minus in front of the answer. Good. So these are this is a pair. Now, what if you do J cross K?
I.
J cross K gives you I. Good. Because again, it's similar. Now, fingers along the y-axis, close them towards the z-axis, and you see it's pointing towards my head, which was in the direction of the x-axis. And again, by the same logic, K cross J is just minus I. And finally, what is K cross I? That's J, yeah. And so I cross K is negative J. Okay.
Isn't it like a circle that you can draw?
Yeah, that's what I was going to say. Right. Yes, if you're overwhelmed by all these formulas, you draw I. It's more like, yeah, like circle / triangle thing. So you write them in what's called like some sort of cyclic order, but that just means that, yeah, if you go from I to J in cross product, you get K, right? If you go from J to K, so you see, if you go from I to J, you get K. If you go from J to K, you get I. And if you go from K to I, you get J. So if you move, what this is, clockwise, or yeah. So this is like, is it clear? Like, so if you, yeah, and then counterclockwise, you just reverse the, put like a sign to everything. Yeah, so I cross J gives you the first formula, J cross K gives you the second formula, and K cross I gives you the third one. So yeah, it's a convenient way to just remember everything. Is that making sense?
Yep.
Good. Yeah, so really this summarizes all those properties. Good. Okay. And then what else should I tell you? Here are some other properties. what's the cross product of a vector with itself? That one is more interesting. So what would the cross product of a vector with itself be? Right. Because again, you make like the clones, 2 copies of you, but then the angle between them would be 0, right? But now sine of 0 is 0, right? That means that whatever you get from the cross product, you get something without size, and the only vector without size is like 0. So you get here not the number 0, you get the vector 0. It's like a bit pedantic of a distinction, but it is a vector. Is that okay? So far, so good. So very important. Well, you get like, right, if you had drawn somewhere like the origin, you like the vector that you get is nothing, right? It's like a point. So it's like the origin, like, yeah. It's the only, right, it's sort of, you get like, you would not get like a vector that you can draw. You would just draw like a point, right? Because you're drawing something without size. So yeah, like if you actually think of like putting the vector somewhere, like for example, here's u and here's v. And then in general, like the cross product is like a vector perpendicular to both of them. So here's like somewhere like u cross v. But what I'm saying, right, like when, yeah, that's a good observation. If 2 vectors are parallel, that's like a more general situation, right? So if 2 vectors are parallel, then their cross product vanishes. So yeah, if u and v are parallel, or anti-parallel, I mean, not that that's too much of a word that is used sometimes, or like anti-parallel, meaning that like one points in the opposite direction of the other, because then the angle would be 180, and sine of 180 is also 0, right? So here, angle equals 0 or 180, then the cross product is 0. Is that okay? So far, so good. Yes. Now, here's another cute property. Anyone remembers the area of a parallelogram? So if you have a base times height, correct. But let's do something cute now. Let's say that the base is represented by this vector. Oh, parallelogram just means that like the opposite sides are parallel to one another. So something like this. Right. So the area of a parallelogram, if height is h, right? what's the base in this case? The base is here, the size of U, right? Is that making sense? Now, what's the height from the picture? Can anyone think about the height? How do you find the height using basic trick in this case?
Pythagorean theorem.
Well, yeah, you could, although that one is a little bit more complicated because you don't know how, you know that the red side, like you have a triangle here where it's H. Here, this is
Or you could do sine. Yeah.
correct. Good, exactly. Yes. So H, right, like the sine of theta equals H over the size of B, right? Is that making sense? Because B is like the hypotenuse. So that means that H equals sine times or V times the sine of theta, right? Is that okay? And so what's the area here? Is base times height. And that's U times normal V times sine of theta. Is that okay? But what is that equal? Like, doesn't this look familiar? What does this remind you of?
The dot product just with the sine.
Well, right, it is a dot product with the sign, but there's actually something that we just saw. This is the size of the cross product, right? That's the norm of the cross product. Right? Because let me go back a second. Sorry. Scroll, here it is, right? So if you want to compute the area of a parallelogram, that's actually equal to the size of the cross product.
So then if you know the magnitude of the cross product, you could also find the direction the same way you would find the direction when you were using the dot product.
Well, there's no, I suppose it depends on what you mean.
But I mean the angle.
Oh, right. Yes, you could also, right, it's you could also use this formula to find the angle. That one is less useful just because the cross product, you'll see it's a little bit more complicated to compute. So it takes more time to find cross products. So no one actually ever uses this formula for finding the angle, but in principle, it could also be used. Yes.
Got it.
It's just, yeah, it's a little bit more tedious. But so like the picture that you should have in mind is that if here's U, here's V, then there's this parallelogram. And so that cross product is a vector whose area is, this is a vector whose size is the area of the parallelogram. Is that okay?
But wouldn't the area be squared and then the size of a vector, isn't that linear? I don't know.
What are you, could you repeat? Sorry.
Well, if you look at an arrow, right, it's a linear thing, and then
Oh, right.
area is squared.
Yes, I agree. Like what you're saying, right. If you were actually to think about units, that's what you're saying, right? The like you're saying like area is like, for example, feet squared, right?
Yeah.
And like, well, wouldn't vectors have like units of feet or whatever, right?
Mm-hmm.
Yes, what I'm saying is that the numbers in front, like, you know, it's like saying 30 feet and 30 feet squared. What I'm saying is that those numbers in front of the units would match with one another. if that makes sense.
Okay,
Yeah,
okay.
like, yeah. You know, in mathematics, you sort of put under the rug, like there are no units. So for example, right, exactly. Like but it's not that different. Like it's just that everyone has already been indoctrinated. But if you write something like x plus x squared, right? Well, you say, well, you cannot really add them if you think that x has units of length, right?
Yeah.
Because then you're adding length with area, and that really cannot be done. But you sort of like, it's like, no, it's like 3 plus 9. Like you sort of like the units vanished. So, but I'm saying if you were actually to keep track of the units, it's sort of like what's written on the chat. Like if the cross product had 30 feet, like length 30 feet, then what I'm saying is that the parallelogram would have area equal to 30 feet squared. Is that okay?
Okay.
Yeah.
Thank you.
No, but it's I am also sympathetic to the units business, and it's sort of hard to keep track of what's going on because like you sort of not even mention them here. But it's sort of what I'm saying is more like the number. It's like a numerical statement that the numbers in front of the units agree with one another. Although it is true that sometimes this is why if you look at the physics books, they call the cross product like an area vector. So they would be actually tell you, no, like you can actually think that the units for the cross product are sort of areas, like units of area. So that like you sort of like take care of that small issue. So sometimes you'll see like in physics books, like the cross product is called like an area vector. Now this actually brings, I don't know if everyone remembers like Kepler's laws, like anyone remembers? There's like a Kepler, one of the laws of Kepler for the planets. Do you study? Yeah, I don't know if people already keep studying this in high school, but there's like a law of motion for the planets, you know, that a planet as it moves in equal times, it strips out the same area or something like that. There's one of the laws. I don't know if you remember, like there's like this area law in one of the 3 of Kepler's law. But now you see Kepler, like area has to do with cross product. So there's really like a cross product hidden among in all of that statement. And it's actually like a statement about angular momentum of the planet. So really like, because angular momentum, if you have seen that, is a cross product between velocity and position. So everything sort of, I mean, there's like a cute story hidden there, but that's you can sort of start finding Kepler's laws just playing around with cross products and other things. Once you know Newton's law of gravitation, you do need that one, which is an important law. So good. But let's do an example. Let's do like example. So let's do this one. Well, let me put it like, let me put it this first. Let's say I have the vector u, which is 2, 3, and this vector v, which is well, it looks even smaller. So let's say that this one is 4, and this other one would be like 2, 5. Okay, let's say you have those 2 vectors, u and v, and this is what I will end up with today. And next time I'll give you like the full formula. So with these 2 vectors, you can form a parallelogram, right? And then like what I'm asking you is like, well, let's find the area of this parallelogram. Okay, so what's the area of the parallelogram? Right, and so the first thing that you can do is like cheat a little bit. Because as I said before, strictly speaking, the cross product is only really defined for vectors with 3 entries, but we can do this thing that we had discussed previously, which is no, like this vector u is really like the same as 4, 3, 0, right? And this vector v is really the same as like 2, 5, 0, right? And so really the parallelogram is still the same parallelogram as before. It's now I'm just seeing it like here on the XY plane. But I just added like a third entry. Okay. And so what is U cross V? Well, U cross V, what is the vector U? That's 4i plus 3j plus 0k, right? Cross 2i plus 5j plus 0k. So far, so good. Is that okay with everyone? There's no point in keeping the zeros, right? So you can just write 4i plus 3j cross 2i plus 5j. Is that okay? And now what I would do is something similar to what we did, you know, with the cross product. I'll just do the multiplications. So I'll do this one, cross this one, cross this one, and then I'll do this one, cross this one, and this one, cross this one. Is that okay? So what do you get in the first case? But now you just have to be a little bit careful with the order. So you get 4 times 2. But then you get I cross, let me write this in purple. So you get 4 times 2 I cross I plus 4 times 5 I cross J. And then on the sorry, I confused the colors. That's easier to fix. I'll be lazy and like change. Sorry about that. And then you get 3 times 2 J cross I plus 3 times 5 J cross J. Is that okay? So far, so good. But you see what will happen, like there's some things that will die now. What is I cross I? It's more complicated than what you were saying, but yes, okay. So I cross I is 0, right? The vector 0, good. And what is J cross J? 0. So now the again, if you thought about this like a sort of an array, the things on the diagonal are the ones that are dying in this case. So this gives you the vector 0. This gave you the vector 0. So there's no point to keep these ones. What is I cross J?
Okay.
K, right? And what is the vector J cross I?
Negative K.
Negative K, good. So one ends up with 4 times 5, right? Which is 20K minus 6K, right? And this is 14K, right? But let me rewrite it like this way, which is like 4 times 5 minus 3 times 2K. Is that okay? That's the same, right? It's 20 minus 6, which is 14, right? but this is sort of suggestive because what were the original vectors? The original vectors, right? U was like, what was U? Sorry, U was 4, 3. And V was, what was V? V was, sorry, 2, 5. Okay, so the thing that we're going to do next time is that you put these 4 numbers into a 2 by 2 array. So you create like a 2 by 2 array called a matrix, which is 4, 3, 2, 5. And then this cute combination of where you multiply this diagonal and subtract the other diagonal is called the determinant of the matrix. And so this gives you the determinant of a matrix. The determinant of A will be 4 times 5 minus 2 times 3. It's basically by definition. I'll give you this formula next time. But like the point that I'm trying to make is that you'll see that you can you get like a determinant of a matrix here in the cross product, and this is why if you have seen the cross product formula before, it is given to you in terms of some matrix and determinants. Okay, so next time I'll like tell you what the determinant of a 2 by 2 matrix is, and a determinant of a 3 by 3 matrix is, and how you can use those determinants to find the cross product. And that's essentially the way in which it is found most of the time. If you want, I can give you, like, since we have 2 more minutes, I'll give you like the formula for the 2 by 2 matrix. Like, the idea is that if you have like 4 coefficient for numbers or for coefficients, then this determinant of the 2 by 2 is AD minus BC. So it's just you multiply these 2 together, you multiply these other 2 together, and the difference between them is the determinant of the matrix. So for example, the determinant of 1, 2, 4, 5 is 1, 5 minus 2, 4, which is 5 minus 8, which is -3. Okay, and the determinant of 2, 1, 3, 3, 5 is 2, 5 minus 1, 3, and so that gives you 10 plus 3, which is 13. Okay, so next time I'll repeat this a little bit more next time. So next time we'll start with matrices. Just say a little bit about matrices and how they are used to find the cross product. Okay. So yeah, see you on Monday. Good.
Professor?
Yes.
Thank you, Professor. Have a nice day.
Have a nice day.
Just a quick question. I was wondering if you could stay on for a minute.
Yeah.
So I was just going to ask you about kind of what's the overview of a regular week for this class? Like, what are some of the things that need to be completed per week, or like just weekly tasks? Because I tend to,
Well,
like, what is the structure from Monday to Sunday in 1 week? Like, is there a workshop? Is there a homework assignment? How does it work?
well, I mean, I would say like you could, I mean, like the easiest thing you could try to do is like if, for example, by this week we have covered most of, there are a couple of things I still have to say, but most of 12.1, 12.2, 12.3, 12.4 in the book, right? There again, like there are a few details that I still have to mention, right? And that's sort of something you can see because at the beginning of every PDF, I write the sections that corresponds to in the book, right?
Got it. Okay.
And then what you could do is just based on those sections, you go to the MyLab computer assignments and try to finish the corresponding section problems of each section before the beginning of the next week. That's something
Mhm.
you could do. Like also, like for example, in a couple of minutes, I'll post the announcement for the next week, a quiz, right? Which is
Okay.
roughly based on the same. And again, like if the quiz problems are from these sections, then it sort of makes sense that you would try to finish the assignments before the quiz takes place. So not that the deadlines are not necessarily coincide, so you may have a couple more days after the quiz if people need it. But I'm just saying, like, that's a good rule of thumb. You could also, I mean, soon, like, it doesn't make a lot of sense right now, but because we still need to cover a little bit more material. But on the MyLab, you'll also see like all the exams posted. So then you can practice those old exams for the exam. But at least on a regular basis, I think that's sort of how you could just like follow the course, if that makes sense.
Got it. So it kicks off with a quiz from last week, and then you probably want to complete your homework assignments before the quiz.
Right, yeah.
And before you do the homework assignments, we've obviously covered the lectures.
Yeah, it's like, I mean, that's, obviously there will be weeks where you're more or less busy, so may not coincide that way every single week. But I think if you just see what sections we were covering during the week and you just go through the corresponding MyLab assignments, then that I think will give you like good sense, like a good pace for like not like for keeping track with the course. Yeah.
Now, aside from the MyLab assignments, is there anything else that we should be completing? Because I know you mentioned the optional quizzes.
Well, those are like the YouTube.
Is that the conceptual?
Oh well,
separate tab?
the conceptual problems, those are like mandatory, but yeah, those you should be completing, but those will be like once a week. What I was going to say is that usually, right, like the conceptual assignment, like in addition to MyLab, you have the quizzes and the conceptual assignments, and so what I would say, what I was going to say is that for the quizzes, sometimes I have posted other extra problems. So on the quizzes, I may just say, oh, go to this PDF, and there are a couple of problems from this PDF. Just work on this for the quiz and things like that. So,
Got it.
Yeah. But right, as things that you have to sort of finish systematically, it's like just like work for the quizzes, like these conceptual assignments and the computer assignment, like the MyLab assignments.
Okay, so quiz, conceptual assignments, and computer assignments. Okay.
Yeah.
And what about the optional thing? That's what you said could be on a quiz potentially, right? It's
well,
like...
every quiz will have like a optional question from a YouTube video. That will always be there. But I mean, it's not. I mean, yeah, that's just to.
Got it.
You should take like 5 or 10 minutes
to go to the next.
Yeah.
To go to the next one. I get it. Okay.
Yeah. I'll post
Thank
like the announcement soon. Yeah. Okay.
Thanks. Take care.
Yeah, no problem. Good. Okay. If there's no one else, no more questions, I'll see you.
So
yeah.
I had a question on the conceptual questions.
Mhm.
So it's having trouble with number 6.
Oh yeah, we can go to that one. Let me open it.
Yeah.
Let me check the screen share. Assignment number 6 is, this one, right?
Yeah.
Okay, so for that one, the thing is like unit vectors. I haven't said this. Maybe I'll mention it on the announcement. But unit vectors mean that the size of the vector is 1, right?
Right.
So what is the size of U cross V? Is this formula that I just wrote a couple of minutes ago? It's the product of the sizes times the sine of the angle, right?
Right.
So you know that the sizes are 1, so that product gives you 1, but you still have the sine thing. You still have the sine of the angle, right, in the formula?
Right.
So it's not.
So that's why it's confused, because
right, you cannot guarantee.
it could sometimes be true and sometimes false.
So it's not true. It is false because in the sense that it's not true all the time, right?
Okay.
Yeah. So I will rewrite it a little bit But yeah, it is false because like if their angle is not 90 degrees, right, then the sine of the angle is less than 1, so you don't get like a
Okay.
good vector again. Yeah.
Okay,
Is that
I was
okay?
just curious.
No,
So
yeah,
I
yeah,
should put
that is-
false for that. Have a great rest of your day.
You too. Bye.